Hi everyone, and I'm actually talking this time for the first time in I think at least a couple weeks. Maybe just a week. Time has been weird this month. I actually had a weird moment where I was just like, man, thinking today it's the end of a really long week, and then I realized it's Tuesday. So that was a weird moment. But anyway, I'm going to explain a little more coding than I normally do. So what we're going to talk about is using monad transformers. Okay. This is partly in preparation for my talk to the TidalCycles meetup on Saturday. Which, I was panicking slightly because, again, I thought it was like Friday. And I was like, oh, I need to finish writing my talk. And then I discover it's Tuesday. So, but one of the things I wanted to talk about is actually like monadic code and then transformers, like monad transformers and things like that, and what you might use them for, and how to solve a problem that's actually kind of bothered me a bit when it comes to sort of the pattern monad. Okay. My dry cough is particularly bad, like in the past few, like 10 minutes, so that's why I keep having to mute. But, the point of these videos is that they're low effort, and I can do them no matter how tired I am. So let's talk. So, first off, let's define a monad transformer. So first off, a monad. What is it? Now, there's a mathy answer, which is fun and interesting, but not like super relevant here. The best way to think of a monad is it's Haskell's way of dealing with state, basically. And by state, I mean, so you know how you can have all sorts of variables in most programming languages, right? And you can communicate between functions by putting values in variables and then reading the values later in the code. Something like Haskell, you don't do that. It is what is known as a pure functional programming language. Basically, code you write must be referentially transparent. It's what does referentially transparent mean? It means that it can't depend on anything other than the actual parameters you pass to the function. There can't be any other hidden state. You have everything that can affect the function has been passed into it. And so, there's a lot of things that make more sense to talk about in terms of stateful programming, particularly once you start dealing with things like, I don't know, I/O, input-output, right? If you start needing to depend on things like key presses in a user interface, well, that's not a parameter that you can just pass in statically and by compilation time, right? Like, it's a dynamic thing. So anyway, monads are Haskell's answer to that. There's anything that more or less you can think of, anything where there's a notion of sequencing code, it's going to be a monad of some kind. And that can be, and so, for example, patterns are a monad. You might be like, well, wait, so what's the sequencing in a pattern? Well, the sequencing is actually the combination, right? Like the way you interleave things in TidalCycles. So, for example, the fact that like you can make the fact that you can say add two patterns together, right? So, for example, like let's do a quick example. So let's choose something, I don't know. And then what we can say is, I'm doing this the wrong direction. So we can say like 0, 1, 2 plus 4, 5. Okay. Or here, let's even like, so the fact that we're combining the two patterns like that, that's kind of neat, right? But like what that is under the hood is really just, I think I used this example in another video, but we're going to go a little deeper this time. Right. This is really what, when you do plus for patterns, is. You're doing something like this, right? And what you're doing is this is a notion of sequencing. Now you're dealing with an operation here that, because it's symmetric, it sort of doesn't. So the nice thing is the way Tidal works with the pattern monad. Sequencing can be permuted, right? This code here is the same as if. So this is one way in which, like, because here, it's the same thing, right? And well, okay, like, I mean, it better be the same thing. Let's act like scientists and check that. Yeah, okay. Yes, it is in fact the same. So because of that, we can sort of permute things however we want, right? But this is still a kind of sequencing, right? We're saying get events out of this pattern and get events out of this pattern. And you can think of it, when you're getting events out of a pattern like this, you're sort of doing it with respect to like a moment in time. And then you're combining them through addition, and you have like, yeah, you just have a nice little way of combining pattern structure. So that's how patterns are. Like, anytime you do something where like pattern interference is what I think Alex frequently calls it, pattern interference. And so basically anytime there's pattern interference, that's sequencing in the pattern monad. Okay. So so the state monad, that's another thing we're going to talk about. It basically gives you a kind of store to, reference in different parts of the computation. Kind of like the way you would shared variables that were like all shared in scope between functions. And it's convenient, right? Like it's useful for doing a lot of things where like you wanted to have control over. It was useful for doing a lot of things where you wanted to have a basically like you could structure your code so that you're explicitly passing the state between every function call, right? Or you can write it the more natural way by having the state be implicit and then called. And the way it's generally called is we have these functions, you'll see them here. That's great. Get and put. Get retrieves the store, or put something in the store. And so one of the things that's sort of fun is, well, how do we do, we're going to combine state with pattern, and we're going to do that with what's called a monad transformer, which is basically a way of creating a stack of monads. And then you sort of take the stateful monad and then crush it down to, like in this case, we're going to take the state monad, and then, you know, at the end of the day, well, what do we need for Tidal's purposes? We need something that will, we'll need something that can return a pattern. So we know pattern has to be on the bottom. So what we're actually doing is we're saying, you know, we're using this type constructor, which says state t, and then we're giving it what state we want, and which is just going to be a double, right? You can have more complex things that have like named subparts and stuff, so it feels like a store of variables. But this, nah, we just want a number. We want the pattern monad at the bottom of the stack. And then we're going to, like, at the end of the day, we're going to return a double. And what are we going to do with this? We're going to use it to solve a problem that has actually vexed me before in different contexts. And that is, how do you deal with pardon me, it's a little late, and only got a couple hours sleep. Again, this is why these videos do not have a ton of editing on them, so I can actually finish them. But so what do we want to do? A thing that has actually vexed me before is the sort of a general problem of integration of patterns, right? Where, what do you want to do? You want to add up the pattern over time, right? The integral. Oof. There's a real problem, though. See, pattern, as a monad, it doesn't have a beginning or end, really, right? It's sort of a infinite stream in both directions, more or less. Like, the interface by which you can understand it. That's kind of how I think of it, right? There's not a simple starting point for pattern to say, like, it's not like a super simple starting point to be like, well, starting from here, add things together. Particularly in a, like, live-coded environment where, like, you can't guarantee you're always starting from cycle 0, right? It just doesn't sort of, it feels against the grain of what pattern is as a data structure. So instead, we're going to use state. And what are we going to do? How are we going to solve the problem? We're going to just define, rather than having indefinite integrals going back and forth through infinity and having no idea whether they converge, and definitely not having a way of telling Haskell how to perform an infinite number of calculations in finite time, although that is a neat trick. Instead, we're going to do a definite integral. And we're going to basically take a range and we're going to add it together. And so the way I decided to do this as an example is we just basically we use a variable this variable n to sort of recursively count backwards to 0. So it's just counting integers backwards to 0. Simple recursion is fun and friendly. And so what happens at the end? When you hit 0, you return what you've put in the store. Aha! And this is telling us how we're going to use the store of the state monad to hold the partial computation. Then, so if it's 0, we just return this. And then where are the other arguments here? Well, n is sort of the number of samplings we're taking. R is for resolution. You know, how far apart the samples are in time, in terms of, like, percentages of cycle. Then, here's the pattern we're integrating. So we use the do notation here, and we sequence, and so it doesn't particularly matter here, but like the same way we showed above with the pattern monad, where sequencing sort of commutes, or at least it did up there, because pattern combination commutes, and if you give it a like just sort of basic pattern combination, commutes if and only if like the operation you're using to combine commutes. And so we had addition there, so it commuted. It didn't matter what order we put things in. But here it matters. We can't put the get before the put, right? These things have to happen in a sequence. So what we're doing is we're shifting the pattern in time. This is my trick. It was, I don't know, it's maybe a little silly, but it also is simple to understand and leads to a very, very short bit of code. And so what we do is we sample the pattern, rotating it through time, so that like at any given moment, like we're taking the rotation through time of the resolution times the number of samples, right? And so that's sort of counting down to the present, but that's fine. It doesn't super matter. And then what we're doing is and again, this isn't integration, like I'm just using that as sort of a metaphor. But we use lift to execute the inner code. So what is this? This has type pattern. Well, we don't have type pattern. We have type state t of double of pattern of double. So lift is the thing that allows us to take the pattern, the thing underneath on the state transformer, and then lift it up. And then after that, we retrieve the current partial computation. We shove it back in with the thing we sampled, and then we recursively call backwards. Cool. And so what you get is, here we're taking 10 samples, 0.2 cycles each. We do a slow sine wave, and we run it by using this eval state t, which is a thing that takes, let's look at this. It takes, for any monad, it takes a state t of the state, the monad, the result type, eats the state, gives a inner monad of the result type. So in this case, pattern of double. Okay. And we're sort of setting the initial store here. So here, I put it 1, but instead, so let's just hear that it is in fact doing the addition. So there you go. We can use the state monad to do things like taking a chunk of a pattern across time, and then doing something by combining all its samplings across time, and then turning that into a new pattern. Kind of a sort of integration over the signal. It's a cute trick. I do have some things I want to use this for, particularly when it comes to the circle music stuff and doing randomized traversals where I only want to move one rotation based off of what the previous rotation was. And so then I want to try and do some stuff like that. And I think some of these state tricks will make that easier than it was, because this was sort of vexing me. But yeah, all that being said, I think there's reasons to actually use like Monet transformers and tidal cycles more often, just to let you do some more like sonically complex things by treating patterns as, um, like just having more sort of stateful or complex things on top of patterns, um, which is should be fun. Again, I'll probably be talking about this on Saturday too, at least a little bit, and hope you can catch that. Actually, there's going to be a few speakers. I'm just one of them. I won't say anything self-deprecating about my relative competence, and yeah. Um, Hope this was useful to someone. And until tomorrow, take care.